me. 5, 2. So this is a weird concept, and another one that was sort of defined before we really knew what we were doing with circuits.
Oh, when was that?
I don't remember exactly when electromotive force was defined, but it was probably at least 100 years ago. So we've got a little basic circuit here, and really basic. There's a battery and a wire, nothing else here. So current is flowing in your loop. So what is causing current to flow? So that's what this whole picture is about. So we know that if you've got the positive battery terminal here and the negative battery terminal here, you've got an electric field pointing downward inside the battery. And what your battery, the chemical composition of the battery, its job is to actually carry charges from the negative terminal to the positive terminal. So it shows in here a little positive charge with forces acting on it. So there's the electric force due to that electric field, and then there's this F sub n force. So that's a force, this chemical reaction force that's working against the electric field to move charges from the negative terminal to the positive terminal. And so that's where this electromotive force term comes from. But this picture is actually inaccurate. It's not really a force per se. And the explanation's kind of long-winded, and I'll let you read the book for the whole shebang. And so we don't really use the word electromotive force anymore. We just reduce that down to EMF. And we say EMF is whatever properties inside a battery that are creating a potential difference that causes current to flow. And so an EMF device would be a battery. So it's any device that's able to create this potential difference that when you connect a wire from the positive to the negative terminal, current is going to flow.
Is there any other EMF device that we can?
Yeah, the one they shoot at your car to short it out. We have EMF devices that we shoot at vehicles.
Yeah.
And it sticks to the car and it shorts out the car.
Wow. That's crazy.
Wow.
Now, I have not heard of that. In practice, the only thing I've ever seen EMF used for is describing a battery. So what does this EMF device do?
Crank it up, high voltage, shoot at the car, boom, it sticks. The whole car just shuts right out.
So
it's like a giant stun gun.
Yeah, for a car.
That's crazy.
We use it all the time.
And this is in the military.
Yes.
Okay.
Yeah,
not just like out fishing. That's when you're fishing, right?
Yeah. Let me go.
Those fish, they just go.
That's interesting. So as far as we're concerned, whenever we see EMF device, we're talking about a battery, basically. So we use this symbol, loopy E. I don't really know. I have a really hard time finding the symbol in the symbols. And so this is my hand-drawn version of the symbol. I don't even think it's a Greek letter, but I could be wrong. But I can't ever find it under the Greek letters. It's not one I ever learned, but anyway, it's a loopy E. Loopy E works for me. The units are volts because it's the battery voltage, right? And we can describe, instead of this outdated version of EMF being a force, we can actually describe it better in terms of the work it does on charges. So we've got this chemical energy inside the battery that can transform that work into physically moving charges from the negative to the positive terminal. So we can describe EMF as a little bit of work done over the little bit of charges that are being moved. get real loopy on those loopy E's.
Look, I got him.
Want to go get loopy?
So there's, I mean, I guess if you're having difficulty with this word, anytime you see EMF device, just replace it with battery in your mind. That works. So we have ideal EMF devices that maintain a constant voltage between the terminals, and they work without any internal resistance. We love ideal devices in physics. We use them all the time. In reality, though, real batteries, real EMF devices are going to have some internal resistance, which we use a little r for. And so this is the battery diagram we've been using. And this one shows one with a little resistance contained inside it. So it's kind of contained in that little orange box, so you know it's all part of the battery. It doesn't matter where you put that resistor in terms of which side of the positive side of the battery or negative side of the battery, it's equivalent. You can put the resistor anywhere, and it just acts like a resistor. It's not a special resistor. When we get to resistor rules, it's going to act like any other resistor in the circuit. Just keep that in mind. It's internal resistance, but we just treat it like a regular resistor. So our ideal EMF device, we can say the EMF equals the voltage between the two terminals A to B. So if you drew your battery like this, so there's the circuit symbol we normally use, and then you kind of put that in a box to say, all right, we actually have battery. It's contained in its little container. There's the battery, no internal resistance. So oh yeah, A and B, right? Those are points A and B. Okay, and so then for our real EMF device, the voltage between points A and B is the EMF minus the current times the internal resistance. So the reason we have to multiply the internal resistance by I is just Ohm's law. Ohm's law is V equals IR. So if we want the units, this has units of voltage. If we want the resistance to have units of voltage, we have to multiply it by current in order for this term to also be voltage. All right, so the next slide, no, that's not the next slide. We're going to come to an interesting example that makes use of this in a second. The next slide talks about devices we can use to measure voltage and current in a circuit. And you already have used one of these in your last lab. We use a digital multimeter, but we used its voltmeter setting. So if you're measuring voltage, we call it a voltmeter. If you're measuring current, we call it an ammeter. But it's all housed on that one digital multimeter device. So ammeters and voltmeters, they're like thermometers. Thermometer measures the temperature of the room, but it itself does not change the temperature of the room. An ammeter can measure current, but it's not going to affect the circuit itself if used properly. Voltmeter measures voltage or potential difference, but it's not doing anything to the circuit itself. So if you see a circle with an A inside somewhere on a circuit, that's a point where they're measuring the current. So that's an ammeter. It doesn't affect the circuit itself. And we always put ammeters in series with other devices. That's when I say if used correctly, you need to put it in series with other devices. Voltmeter, a circle with a V inside, and we always put a voltmeter across the device. We want to measure the potential difference across it. So even the way we describe potential difference, we say the potential difference from point A to point B We're talking about across the device. So if we wanted to measure the, well, let me draw a different circuit over here. Try and be neater. Okay, so an EMF device and a resistor. Let's say we want to measure the current that's running around this loop. Where would we put an ammeter? Ammeter measures current.
In series.
In series.
Just grab that node right there on top of the
Up here?
Right.
Okay.
and another node over there.
Okay. Okay. So we'll just put it right in line here with the wire. There's an ammeter. Now let's say I want to measure the voltage drop across this resistor. Where would I put
On either side.
across? Yeah. So it's, when I say across, it looks like it's in parallel now with this device.
Is that inside?
I can, if I can move the wires like this. Oh, inside?
Yeah.
Yep.
Okay.
It's all functionally equivalent.
Okay.
Yeah, that all works. Okay, and again, you'll get practice doing that next week. Okay, so the next task, we're actually putting together sort of imaginary circuits, and we're going to solve for various properties of the circuits. So a single loop circuit is about the easiest thing you could set up. It's basically what I drew here with one resistor. Now we can add multiple resistors in series, and it's still a single loop circuit. So the first thing we need to know, say our goal, this is typically the goal of a single loop, or any of the examples we're going to see, is to find the current in the loop. You can rearrange Ohm's law and probably solve for other things, but let's say our job is to find the current in the loop. So the first thing we need to know is this Kirchhoff's voltage law. We also call this the loop rule, so we don't have to say Kirchhoff's every time. So for any complete loop in the circuit, the sum of the potential drops across each device around the loop must equal 0. That's the rule. So here's a loop, and we've got a 12-volt battery or EMF device with internal resistance of 2 ohms. So this whole thing is the battery. We've got a 4 ohm resistor, and that's it. Actually, that's a little bit like this one, except we don't have internal resistance on our battery. Notice that the direction of current is going counterclockwise. That's because the positive side of the battery is on the right, so we're always going, current's always flowing away from the positive side. Okay? So we will evaluate this step by step on the next slide. So we're going to start in the bottom left corner of this circuit and walk all the way around and look at voltage as we go around. So when we're on the negative side of the battery, that's basically ground. So last week when we connected the voltmeter to the negative side of the battery, we got 0 volts. So when we start on this left side of the battery, we have 0 volts. When we go across the battery, the EMF device, the whole properties of the battery is that it creates this potential gain of 12 volts. So we jump up to 12 volts in this little space across the battery. And anytime we're just walking along wire, there's no drop in voltage because we're assuming the wire doesn't have resistance. So we stay at 12 volts until we hit the internal resistance of the battery, which we're treating just like a regular resistor. And it's 2 ohms. So this circuit already tells us that there's 2 amps of current flowing through it. So if we multiply 2 ohms times 2 amps, we get 4 volts. So when you go across this little resistor here, you have a voltage drop of 4 volts. And then we've got wire again, so nothing changes. You're going to stay here at 8 volts until you hit the next resistor. It's a 4 ohm resistor, so what's the voltage drop? 8, yeah, 4 ohms times 2 amps gives us an 8 volt voltage drop, which brings us down to 0, which is good because we don't have any other devices until we get back to where we started. So we start at 0, we climb the mountain, we go down, we get back to 0. So a nice way to think about walking around a single loop and the voltage law is like if you took a loop trail hike. There's a crazy one in Eagle Creek Trailhead in the gorge. If you guys ever do that, it's an awesome hike. There's like 7 waterfalls in a 2-mile stretch.
Like that famous one that's on the album. And all that.
Yes, the one that's like V and then it like just funnels the water and there's rocks. It's beautiful. But there's a nice loop that you can take. So you climb up elevation, you go to the very top of the gorge, and then you come down a different pathway. And when you get back to the parking lot, you start at the same elevation you started with. So that's the idea. Whatever voltage gains or elevation gains you make, you're going to have to make those same elevation drops if you want to get back to your starting point. So,
Cool water slide.
or a really cool water slide. So the way we can describe this circuit using Kirchhoff's voltage law, I can redraw the circuit on the board really quick. That's it. And so say we don't know the current here. Then Kirchhoff's voltage law says we get plus 12 volts from the battery. Maybe I'll just call this R1, R2. So plus 12 volts from the battery because we're going to go in the positive direction of the battery. And then every time we go across a resistor, we're losing voltage. So it's I times R1 minus I times R2. And that should get us back to 0. And so functionally, this is what we solved. Let's say we didn't know current. We can rearrange this to solve for current. So you have E equals I, R1 plus R2. And then solving for I, you'd have E over R1 plus R2. So this is our loop rule equation right here for this circuit. And we're going to get a whole lot of practice writing these, so if you're a little befuddled about everything, it'll hopefully become crystal clear after doing it 10 times. All right, so sign convention, I almost thought about cutting this slide out because it can be a little confusing. So typically if you've got one battery in your circuit, you're going to not have any confusion about what direction the current is flowing. The current is going to be flowing away from the positive side of that battery. And so our loop rule equation is going to be going in the direction of current. So that's hunky-dory. Let's say you've got a circuit with 2 batteries. And they're facing opposite directions. So E1 and E2. And you don't know the values of E1 and E2. If you did, whichever battery is bigger is going to be the driver of current. So if E1 is bigger, it's going to drive current clockwise. If E2 is bigger, it's going to drive current counterclockwise. But if we don't know, we just arbitrarily pick a direction. So we pick our direction that we think current is going to go. okay? It's all right, because if we get a negative value for our current, we just know we chose the wrong way. We just change the direction and make it positive, and it would be the correct answer. So choosing an arbitrary direction is just fine. So our loop rule equation, if we decide that the current is going clockwise, then we're going to walk around this loop clockwise. So we go across the battery in the direction of the current that this battery would want to drive, and so you'd have a plus EMF for that device. Anytime you go across a resistor, it doesn't matter which way you go across, it's always a voltage drop. So it's always minus I R1. And then we decided to go clockwise, so when we go across E2, we're going in the direction that this device would want to push. It's opposite to what this device would want to push. So there would be a voltage drop if we go in the wrong direction across that EMF device. Okay?
So that's question. Those are the two that are questionable, depending on our distance. I mean, which way we picked.
We chose to go clockwise, therefore this one's going to be positive, this one's negative. Yeah. And then when we go across R2, every resistor is always minus IR. Okay, so that gets us back to where we started, so the loop rule equations should equal 0. And so you'd have to have more information here in order to solve this. Obviously, if you have two unknowns, then you can't really solve this. But that's just functionally how we would write the equation in that case. So that's essentially what this slide is all about. If you decide to go across the battery in the same direction that it wants to push current, then you have a plus voltage drop, or a gain in voltage. And if you go across the battery the wrong way that it's trying to drive current, then you'd have a negative voltage. Okay, those of you who have taken circuits, I know you guys do it differently in circuits. That's okay. I'm not asking you to relearn your ways. Do it whatever way you do it. But don't spread those methods to everybody else, because I don't think they make very much sense. So
I think everybody kind of almost does it their own way.
Yeah.
So much too.
And I'm sure every teacher is going to teach it.
Homework, I'd be completely lost.
Yeah, I mean every teacher teaches it differently. So I guess if you're helping someone that hasn't taken circuits before, just go with what we're trying to teach here to avoid double confusion. Yeah, that was like my dad in 8th grade trying to help me with my math homework and saying, well, you're just solving everything wrong. Let me show you the way I learned. I'm like, don't do that. Just help me do it the way I learned, because I kind of get that. I don't want to learn two methods that I don't get. Okay, anyway, anecdote over.
We do it wrong, let's do it the physics with it.
See, I think it's fine if your kids appreciate it, but with me and my dad, it was just like this, and so I just, oh really? See, I just stopped asking him for help.
Like Dad quit. Just confusing me.
Yeah.
And she's 16, so.
Yeah, much better to let her figure it out.
Yeah, I just stopped asking for homework help after 8th grade. Too many yelling matches. Me yelling, my dad walking away.
Sounds about like us.
All right, let's try example 25.5. I jumped way ahead here. All right, so I'm going to redraw this circuit on the board given the information I give, and as always, the book solution isn't walking through every little step, so just kind of, I know, well the book likes to skip to the very last step and not really tell you how they got there, so hopefully I can fill in the details. Okay, so ignore the picture for a second and look at the board. We only have one battery in this picture, so what direction is the current going to flow? Counterclockwise? Okay. All right, so that's direction of current. We don't know current, and we want to find the voltage across the battery and the current running through this circuit. So let's start with Kirchhoff's voltage law. So let's start at, I always like to start on the negative side of the battery so that when we go across the battery, we get our big positive gain first. So walk me across around this loop and tell me Kirchhoff's, our loop rule equation.
R times I.
Minus R times I.
And then minus R 4 times I.
I'll just put big R. Okay, equals 0. Okay. Does everybody agree with that, or does anybody have any questions?
Let's do the loop one more. Start from where you started.
So we start at B,
Okay.
and we go across the battery.
Oh, okay.
So that's plus 12. And then the first resistor is minus I times little r. And then we come all the way around here until we get to the next one, which is minus I times big R. And then we cross the ammeter, but the ammeter is just the thermometer. It doesn't affect the circuit. And so then that brings us back to point B.
I didn't know where you started. That was kind of like, oh, I didn't catch it. How do we know where to start?
Wherever you want. You can start wherever you want, and you'll get the same result.
Then what's the difference between the big R and the little R? There's
So
two resistors.
little r is internal resistance, so that tells you that that's associated with the battery. Functionally, it's just like any other resistor. So you can, you just, when you put in 2 ohms here, it's not going to look any different than here when you put in 4 ohms.
So it's just because there's two.
It's because, little r because it's part of the battery. If there was 2 regular resistors, I call them R1 and R2.
Oh, I see the other one doesn't have, okay.
Yeah. So if we wanted to find current here, so let's plug in our actual resistor values. So minus I, little r is 2 ohms, big R is 4 ohms. So now our only variable is I. So when we solve for I, what will I equal? I mean, give me the equation with numbers before you actually solve. 12 divided by 6. Okay, so 12 volts divided by 6 ohms. And what is 12 divided by 6? 2 amps, okay. Okay, so that's what our ammeter would read. And we could put the ammeter here, it would read the exact same thing since the current is the same all around this loop. Okay? Now the voltmeter, way up there, so that's a little bit trickier. So the voltmeter, I'm going to write the voltage across the voltmeter as being the voltage from point A to point B. And we know that this line is parallel with this line. So just like we learned with capacitors, things in parallel have the same voltage drop. So this is VAB, and then this would also be VAB. So the voltage drop from across this line would be whatever the voltmeter reads. So what's the voltage drop from, let's see, A to B? Actually,
B to A or A to B?
B to A.
well, they give us a positive answer. So let's go from B to A. So we're just, it's like Kirchhoff's loop rule, but we're stopping after we get to point A.
4 volts.
Okay, so we had 12 volts minus IR. And I, we just solved, was 2 amps. And little r is 2 ohms. Okay, so we've got 12 volts minus 4 volts. And that gives us 8 volts. Okay, so that's what our voltmeter would read. What if we put the voltmeter, we moved it so it was reading across from point A prime to point B prime? Same thing. Why, Derek?
They're parallel.
Yeah, so everything is in parallel. Yeah, if we put it down here, it would still be in parallel with that battery. It's also in parallel with this line, and so this line would just be I times R, so 4 times 2 would be 8 volts as well. So if people are not quite seeing that. So for this one, V A prime B prime, you could write as I times big R, 2 amps times 4 ohms gives us 8 volts, and we double check that that AB does in fact equal VAB A prime B prime. All right. Okay, any more questions about single loop circuits and just calculating current for those? Okay, so the last few slides before we break for lunch, maybe, well, we'll see how far we can get, is about power in circuits. And so this is just a little smattering of what we're going to talk about. We're going to talk about power at the end of chapter 26 as well. So this is just a taste. So again, we're looking at a single loop circuit. Here you've got some kind of device that has resistance. So it's not necessarily a resistor. Let's say it's a toaster. A toaster is going to have some kind of internal resistance. We don't know what it is. And so if we mark the top of that device as A and the bottom of that device as B, and we want to figure out what the resistance of that device is, we know, very similar to this problem, that whatever the voltage gain from the battery is, V battery, would be the same as the voltage drop across this device, VAB. And then inside the device, we can rearrange our current. This is our definition of current, was I equals dq over dt. So there's moving charges. So then going back a couple weeks, we talked about electric potential energy. It's been a while, but electric potential energy we defined as V times Q. I think we solved for V. We said V was equal to U over Q. Yeah, so we're just rearranging that. And so we have U is equal to V times Q. But we put the D on them, so a little bit of energy of current. So if we're moving current, you're using energy to move those current through this device. Then you've got a little bit of energy to move a little bit of charges times the voltage drop. And so replacing dq with I dt, we get this relationship. And power, we've seen power come up multiple times in physics, and it's always some combination of energies, but it's always energy over time. In this case, the energy is the electric potential energy to move charges. We plug in this relationship we just derived for potential energy, and so you got dt on top and dt on bottom, they cancel. And you get this really nice equation for power. Power is just I times V. So a whole lot of calculus to get us this really simple result to solve for power. So if this is a toaster, and you wanted to know what's the power rating of that toaster, say you look on the back and it's like an 800 watt toaster. Where does that number come from? This is where it comes from, so I times V. What's that?
Why do electricians use E? They don't use V. Like it's P equals I times E? Is it just because they don't want to confuse E with electric field in physics? Is that why they don't use the same?
I have no idea.
Yeah.
There's a lot of things that like engineers, like symbols or words that engineers use that's different than physics, but it's the same thing. I mean, I don't know. I think even when you guys do the loop rule in circuits, you do it differently, and I don't know why engineers do a lot of things the way they do. You'd have to, well, I don't know that an electrician's gonna know the answer to that question, but you know who might would be Christina Crespos, because she's an engineer and a physicist. So she might know the reason.
Maybe it's like that E is already electric, field. Maybe there's just some confusion if they use E for that.
Maybe. I mean, there's so many things that we like to repeat variables so many times. So we use E a lot for a lot of things too. They use capital E for voltage.
E equals I times R. That would be the
Oh.
And they use pi, which is P equals I times E for power.
Pi.
Yeah. So there's the whole pyre wheel. You ever seen the pyre wheel? It's got all the.
I have.
I had a teacher that had a tattooed on top of his head.
Really? Okay.
So he'd shave his head, you could see the pyre wheel, and then he'd let it grow out, and you wouldn't see it.
That's so funny.
Yeah, but he could, what do you have to do? He'd have to go to a mirror. I mean, seriously, I'm talking about. Get someone to read it for him.
Yeah, like,
What's it say?
I'm sure he had memorized.
Oh, it'd
That's
be
interesting.
to find out when he had that done and the state of mind he was in.
he was in the military, I think, at the time.
Well, there you go. Okay.
Hey.
My daughter is, that's not what I mean.
Oh, you'll agree, Saban, that there's a tattoo culture in the military.
Yes.
I mean, it's like you got to have a tattoo. It's just what are you going to get a tattoo of, right? It's like everyone's getting a tattoo. Well, I guess I'll get the power wheel because
Yeah, there we go.
And now the new rule is you get a tattoo, you can kick out.
Yeah, you have to get it, well, you can have
it's
it.
in a
so you don't
hidden
see
place.
it.
They
Yeah.
cannot be seen.
Yeah, exactly. Oh, yeah.
And now they're rolling up their sleeves, so.
Yep.
For the summer months, we're authorized to roll up our sleeves, but if you have tattoos that show you're gonna have to sweat it out, you can't roll up your sleeves.
Yep. So people are shooting at you, and they're worried about your tattoo.
Exactly.
Come on.
It's an appearance thing, yeah.
It's a sequester thing.
Yeah. No truth. My daughter's okay. I'm just saying that,
Let's see, current amps.
Yes.
You think so?
I is just easier to remember than PIV.
PIV. Well, there's more to come. So this is one equation that's useful for power. And this can be used for any device. So this works if you've got a capacitor or a resistor or a PN junction or anything. This is our power equation that we can use for, in general for circuits. Or general would make more sense. And then we've got some versions of this for resistors only. Since we've got Ohm's law, V equals IR, you can replace V with IR, and then you'd have power equals I squared times R. Or you could rearrange Ohm's law, I would be V over R, yeah. And so then you'd have V squared over R. Obviously, those equations are only going to help if you have a resistance to plug into them. So that's why they're for resistors only. All right, so that's power for us. Let's see examples 25.8 and 25.9. Still on. Darn. I erased it. Okay. Example 25.8 says, for the circuit we just analyzed in the last example, find the rates of energy conversion, chemical to electrical, and energy dissipation in the battery. The rate of energy dissipation in the 4 ohm resistor, and the battery's net power output. So this is the book's way of saying, do you understand verbally what we just described in equation form? So right now, probably not. So let me add this to our power conversation here. So when you see rate of energy conversion, like basically whatever is happening in the battery, that's the chemical to electrical. They're asking you for the power of the battery. If they ask you for the rate of energy dissipation, that's whatever devices are using up energy. And so the ones that use up energy are resistors. So that would be the power being consumed by the resistors.
But isn't one of the resistors like a part of the battery?
Yeah, and we'll have to account for that here.
Yeah.
And then the battery's net power output. Oh yeah, okay, good. Okay, so Saban's point, the rate of energy conversion, this is the EMF device part. So this is the ideal EMF part that's doing the work to actually move charges. So this would be the power of just the EMF device. The last part of this question asks us for the battery's net power output. So this would be our the EMF device and the internal resistance inside the battery. So another way to write that is just P battery. And so when we actually solve these, then it'll make a lot more sense.
I guess my understanding of it was that the last one, the net output, would be minus the internal resistance, but the rate of energy conversion would be the total, including the internal resistance?
Let me just double check, because I thought I had it the other way around. So what's up here is correct. So it says on the solution to this, it says the rate of energy conversion in the battery is 12 volts times 2 amps. So I need my circuit up here so we know what I'm talking about. So there's the whole battery. And this was my EMF part, the 12 volts. So when we solve for the rate of energy conversion, they're solving for just 12 volts. Let's see, I times R. Make sure we are all on the same page. I times V, 2 amps times 12 volts is 24 watts. So that's the first, just the rate of energy conversion. And then the total power of the battery would be I times V battery. And we said for a real battery like this, V battery would be E minus I little r. So 2 amps, 12 volts minus 2 amps times 2 ohms. And what does that give us? 16 watts. So if it was a perfect battery, we could get 24 watts from it. Because there's just 2 ohms of internal resistance, we only get 16 watts out of it. All right, and so the last question was the rate of energy dissipation in the resistor. There's only one resistor. R was equal to 4 ohms. Oops, it's supposed to be a P. I like writing R's apparently. Okay, so how am I going to find the power dissipated in the resistor? I squared R? Okay. Okay, so 2 amps again, square that. R was 4 ohms. And what do we get, Jacob?
16 watts.
16 watts. All right, so we've got 2 values that are 16 watts. Does this make sense? Jacob, why does it make sense? Other Jacob.
Because you, in the circuit, you have to use up what power you produce, so they have to be equal.
Okay, so this was functionally how much power we get from the battery. That must be equal to how much power the resistors are using.
That's like the loop rule thing.
Yeah, it's kind of like a consequence of the loop rule. Okay, any questions about this problem?
Very weird.
Yeah, and that's
part of the whole battle of the whole problem.
yeah, it's half the battle of the book is like just
Translating.
what the heck they want, and they love to say rate of da 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 instead of just asking for power. So this is something I would put on my equation sheet if I were you. Okay, 25.9. We've got the same circuit right there, but we're going to put a 8 ohm resistor into that circuit instead of a 4 ohm resistor. And so then it says, how does this affect the electrical power dissipated in this resistor? So what would change about this circuit if we replace this 4 ohm resistor with an 8 ohm resistor?
The increase.
The increase.
The resistance.
This was, yeah, a bigger resistance. The current would decrease. Yeah, if there's more resistance, then there's less ability for current to flow. Okay, so the first thing we have to do is figure out our new current. So how are we going to find the new current if we've got 8 ohms instead of 4 ohms?
Change it to the 4 to 8?
Yeah, in what equation? How do we solve for current?
Do your whole loop rule all over again.
The whole
Yeah,
thing?
do the loop rule all over again. Okay, so let's do our
Can't
loop
just
rule.
plug it into any of those then. Oh, bummer.
Right, because this equation requires knowing a new current. We don't know the new current, so. So what's our loop rule equation? If this is now, we replace this with 8 ohms.
Plus 12 minus little r I minus 8I equals 0.
Okay. Okay, and so we've got 12 volts minus I times 2 ohms, that was our little r, minus I times 8 ohms, that's our new r, equals 0. And then we rearrange this to solve for I, and we'd end up with what over what?
over 10.
Yeah, so 2 ohms plus 8 ohms, 10. Okay, so 12 over 10, what's 12 over 10? 1.2. All right, so Elaine was correct. This makes our current go down. So the power due to just the energy conversion would be what if our current is now 1.2 amps?
1.6
For the 8? Oh,
So you put the I,
Yeah, so for this equation, we're going to replace 2 amps with 1.2 amps. What would we get?
14.4.
Okay. And then the power of the whole battery, how would that change?
.6 watts.
Okay, and then the last one was the power dissipated by our new resistor. So we've got a new current and a new resistance. What's that going to do to our... Actually, you guys can guess without even plugging in numbers.
9.6 watts.
Yeah, it should be
It's
9.6.
yeah,
Yep.
I was just looking through that going,
Anybody double check and verify that? Or you trust physics?
wait, so then, okay. Yeah, so, in the battery one, the 12 volt minus, then it'd be the 1.2 there, okay.
Yeah, 1.2 here and 1.2 here. Mhm. All right, so any questions about this one? Seems like you guys, for the most part, have everything figured out. And we're at a really good stopping place. We just finished chapter 25. So let's do our lunch break now. So it's about 11:50, so we'll come back at 12:20 or so.
Turn off.
Yep.